I'm here to talk about the DVB S2 and DVB S2X block party going on all this week. We have our own room. It's in CRSC. So go out and around towards the workshops. Keep going. We're on the end. This is hosted by Phase 4 Ground. So who am I? I'm a ham, W5NYV. I have a master's in information theory from USC, or a master's in Icky Math. I'm active in the Info Theory Society, and recently co-founded something called Open Research Institute. This is a research institute for open source work. One of the co-founders is Ben Hilburn, the president of GNU Radio Foundation, and the other co-founder is Bruce Perrins, an open source activist. We did this in order to provide a structure for the work we were already doing. It's to promote and publish open source and open process and open access work. A lot of what we do is amateur radio related work, but it is not exclusive. Our other projects are something called open cars. As you know, autonomous vehicles are a big deal. And we think that there should be more open source work in this area. And another part of our work is open codecs. So Roatel is somebody that we're trying to help out. He is responsible for Codec 2. So that's Open Research Institute. Phase 4 Ground is one of the projects. I'm the lead of Phase 4 Ground. And we are a project devoted to an amateur radio broadband microwave system that takes DVB S2 and DVB S2X, which are digital video broadcast standards, to open source them for amateur radio use. This is planned to be an uplink on 5 gigahertz, so it's channelized, frequency division multiple access uplink, and a time division multiplex downlink. That's where the DVB comes in. The uplink is not DVB, it's a little simpler. So since those are central technologies to our project, we believe that these receivers for DVB S2 and S2X need to be in GNU Radio. And so a lot of our current work is devoted to get that reference design into GNU Radio, to get enough of it into MATLAB as a reference design to move into FPGA, and to allow you to run GNU Radio on all the different awesome SDRs out there in order to participate in our particular radio system and spread it around and use it. We intended for this system to be used for payloads, for AMSAT payloads, or and you'd be able to use this to communicate through the satellite. You can also use this terrestrially, and that's probably where you'll most commonly find it. So in discussions of DVB S2 and S2X, the reason why, or the main reason why the receivers are not currently in GNU Radio is because the decode process for the forward error correction is really pretty hard. It's low density parity check codes, and that's the part that we are currently working on right now. And when I say we, I say Phase 4, and this is Phase 4 Ground, and we actually have started an open source payload project. LibreSpace, Satnogs you heard from this morning, are our buddies and are encouraging us and helping us. This space part has just kicked off, and the ground project has been going on for a couple of years. These are sponsored by and helped by Open Research Institute. So what does a radio system look like? Here's our uplink and downlink, and the type of uplink and downlink. And you can see here we have the uplink channels from all different, combined, multiplex in the payload, and comes down. The neat thing is that on 10 gigahertz, you can have a broadband signal. The regulatory problems that the previous speaker talked about, well, that's why you need to go to microwave as an amateur. They don't exist there, or they exist in a different form. If you want broadband digital, you go to microwave. That's where we went. The neat thing is that in this amateur band at 10 gigahertz, the terrestrial and space subbands are right next to each other. So with a little bit of RF magic, you can have one radio that will work terrestrially and for space. So what have we been up to besides all this LDP stuff? Well, Phil Karn is here, and you should talk to him about his SDR package. It heavily leverages and enhances and uses IP multicast to have a distributed software-defined radio. We love it. We need a correlator for DVB, and so we've been working on that. At first, we thought we would need to do our own special DVB-S2 correlator and have it as a block in GNU radio. What we now think is that we need to go and take the correlator estimator block and, rig it up to where it can be used for our project as well. As I said, the open source LDPC decode is the tricky part. We do have an open source version right now in our repository, and it is written for GPU. And the reason why is because we're a team of volunteers. There's about 200 people that are interested and support the project. Active developers number about 20 right now. And as you know, working on GNU radio, this changes and evolves over time. We have new people come in that can give time and leave. So this has been pretty stable over about 3 years. We've been very lucky. The volunteer that took on the challenge of actually writing the decode wanted to do it on GPU to learn graphical processing unit. So it's in CUDA. There is kind of a caveat there. You have to have all the frames in parallel. They all have to look the same. And that may not sound like a big deal, but it is for DVB if you want to use adaptive coding and modulation. Therefore, your GPU is good for if you have all the same data. It works, there's a few little bugs in it, but we have it and we've published it. What we would like to do is to take that code base and move it to an FPGA and also have it in MATLAB. So that there can be several different implementations that don't have that caveat. We've developed a dual band feed. If you look at the frequencies that we use, 5 gigahertz up and 10 gig down, you may notice that there's a second harmonic problem. We don't want people to have to use 2 different dishes and all have to point 2 different dishes. That's kind of hard. If you want to, you can, but it's much better to have 1 dish for this particular type of system. In order to have 1 dish, you need to have 1 feed that handles both. That's pretty much the best. And so we took on the challenge, and we successfully designed a dual band feed. And that's also in our repository. We've done some work on something called GSC. Now, if you're thinking DVB, digital video broadcasting, it's used for satellite television, you're like, well, that's MPEG. Woo, great, MPEG. We take that out. That transport stream in DVB protocol can be lifted out, set aside, and you take another DVB protocol called GSE, or generic stream encapsulation, you move it over and you drop it in. You don't have to put up with the overhead of MPEG at that point. And another big benefit, besides getting a little bit more throughput, is that you can now send generic data, IP stream data, through this GSE channel. So we tackled that, and we published some work. We've got generic stream encapsulation in Wireshark, and it's in GNU radio as well. So getting everything ready in order for you to be able to use GSE and just to have a data pipe instead of having to use MPEG format transport stream, that's a win. We have filter work. We've published some filters for 10 gigahertz. We have some 5 gigahertz amplifier and RF work. And then ARAP demonstrations, and I'll show you what that is in a bit. This is an amateur radio access point. You may be thinking, wow, 5 gigahertz, can I go to HRO and buy that radio? No. This is all pretty much do-it-yourself, custom, or take an SDR and get it to work. But we're like, well, okay, what if you have an HT on 2 meters? Can you participate in this system? With a little extra work, you can. What this does is it listens to the 2 meters, packages it up for the uplink, and sends it as tagged data so that we can tell that you're a legacy radio. We did this because we were really impressed with the way that Yaesu System Fusion does it. This is an amateur radio system that has automatic mode recognition, and whether you have an old analog HT or the new fancy digital, it's P25 with a little bit flipped, but whether or not you have either one of them, it'll just accept it and pass it to the repeater. We thought this was a great way to not cut off a whole community, a whole huge number of working radios. And we said, okay, we'll go ahead and take on that challenge to be able to support legacy radios. We're also having tons of fun. Working on any of this stuff really is fun, and it's just a wonderful group of people. Everyone is welcome to join. We have a mailing list and a Slack and a GitHub, all the standard triumvirate of things for open source right now. So everyone's welcome to join us. We're also buying every SDR dev board that comes along. So if it's on Kickstarter, one of us has probably bought it. And we're throwing the block party here. So you can meet us in person, and if you can contribute to any part of DVB S2X, you're more than welcome. So here's the ARAP, just as sort of a visual explanation. This would be a device on the ground that listens to whatever we decide that it's going to be listening to. Probably in analog radios. You want to support a population, or you need to deploy in an emergency and support emergency traffic and get it up to a satellite and get it out of an affected area, then this would be a good way to do it. There is competition here. There are devices that actually already do this, but they're from Motorola and they're extraordinarily expensive and they haven't changed in 25 years. We think that with the amount of change in SDRs that has happened over these decades, that this could be done for a lot cheaper. So just a visual representation of what we were talking about. So before I tell you a little bit of the technical side, I'm going to focus on LDPC because that's kind of if we can solve LDPC and get that decode working, I hesitate to say that the rest of the system like this is easy, but this is really the tallest nail. But in terms of what I've told you already, is there any questions or anything that you would like to hear more about or that I've missed? Okay, cool. LDPC, or low density parity check codes, they were discovered in 1963. It was a PhD paper by Robert Gallagher. This was very impractical to implement, so it was promptly lost or forgotten. It's probably more accurate to say that it was deliberately overlooked and set aside. Gallagher coded his ideas up and ran them on an IBM 7090 in 1963. The block length was only 500 bits. It was simulated with a very large probability of error, and just used one code word, the all-zero code word. Just that demo took hours and hours to run. So you can tell at the time, this type of forward error correction was not going to be implemented or deployed. So it was lost until the early 80s. Michael Tanner, if you know about Tanner graphs, he looked at it, and the Tanner graph is based on his work looking at Gallagher's stuff and saying, wow, low density parity check. Okay, I see a way to do this. So it rose to the surface, and it was immediately lost again. It was still very impractical to implement, just took too much processing. There just wasn't enough parallel processing out there to do it. In 1996, it got revived again, Sir David McKay. This is a paper that we all read in this particular field. And this time, it started getting some traction. We finally had enough processing power to implement it. It was chosen for DVB S2, Satellite Second Edition, in 2003. That's its big break. It had been used for a couple of other things, but ever since 2003, LDPC has slowly taken over a lot of areas in forward error correction. It surpassed turbo codes in error floor and performance, and it works better at the higher code rates. If you have a low code rate or a short code, then you need to still stick with turbo. How good are they? They're a fraction of a dB from the Shannon limit if you use long codes. And these aren't codes that are useless or just in a paper. They're actually implemented and used. The ones that are still really too long to have an implementation or an application are really only a few hundredths of a dB away from the Shannon limit. When I say Shannon limit, that's pretty good stuff right there. Some other advantages: they don't need interleavers and they don't need a trellis on the decode. You can parallel the decode. Great error performance. Error floors, not so bad. Decoding complexity increases linearly with the number of ones in the matrix, so the sparser the matrix, the better. And it's good for many channel models. That's kind of a big deal. So in DVB S2 and S2X, we have something called adaptive coding and modulation. And what this means is that you take in the signal-to-noise ratio, and you decide what your coding and what your modulation is going to be in order to maximize that bit rate. Your symbol rate is fixed. And so the seesaw of bit rate and code rate and modulation, it's sort of like a fulcrum. So you're getting the best possible throughput for the channel conditions at that particular time. Okay, so Every presentation should have that one slide. Like if you're told you can only have one slide, and this is mine. This dark line here is what we call the Shannon limit. Along the bottom, this you can think of as SNR, signal to noise ratio. So over here, we got a big booming signal. And over here, we have lots and lots of noise and a tiny signal. This, the vertical, is going to be how many bits you can cram through that channel. What's the bit rate you can get? Most systems are designed where you pick your worst case SNR. For example, a terrestrial microwave link or your amateur repeater site. And you're like, well, the worst case is probably going to be in the summer with lots of foliage and it's blocking things. And well, okay, what's my worst case? You pick it, maybe in the middle of this graph. You go up, you hit the Shannon limit, you go over to the left, and you find out that's your max capacity. That's your max channel capacity. So if you've ever heard of capacity and information theory, that's what you're seeing here. This is a lovely result, and it made a lot of things come totally clear when it was discovered. Now, these little herky-jerky things, these are all the different combinations of modulations, all the different modulations, and all the different code rates in the DVB and DVB S2X standard. You can see you've got lots and lots of choices there. And look how close it is. And I stole this from AHA. They're our friends, so I hope they forgive me. They have the Shannon limit, and then there's the spec, and you can see that there's their core, and running on an EDIS SDR. So you can see that it's right on spec, and it's extremely close to the limit. This is why we put up with all of the hard math in LDPC. We want this. We want to be able to have this agility as amateur radio operators. It's just so cool to be able to squeeze out every last bit that you can get of capacity. Now, you can't go here, right? This isn't any good, even though it'd be great to have maximum bit rate at maximum SNR. You have to stay in here. But that's okay, because that's where Hello Kitty is. Here's what a Tanner graph, that Michael Tanner guy, this is his big innovation, and this makes it a lot easier to deal with LDPC codes. It's called a bipartite graph. You have a group of nodes over here, and you have a group of nodes over here, and you have edges that connect the graphs together. These are really, really useful if you have a nasty, nasty function, some sort of function with lots and lots of factors in it, and you need to decompose it to make it tractable. So, each of these over here, these square things, because I know, I'm sorry, there's multiple screens, but there's only one laser. Sorry about that. But the square nodes might be the factors of that nasty function. And then they are each connected to the variables, the circles. So this top one here would be a factor, and it's connected to two variables. Really, really neat stuff. Graph theory, it might look a little scary, but at least it's pretty, and very, very useful for that sort of thing. So how do we get a graph out of a big matrix? And I mean, LDPC matrices can be really, really large. And they're called low density because they don't have a lot of ones. If it's not clear, these are all binary matrices. The entries are either 0 or 1. Usually a H is going to stand for the parity check matrix, the thing that you use to decode. There's another companion matrix called a generator matrix. And in most forward error correction, you actually start with the generator matrix. Like if you've ever taken a class in code theory, you start with G and you end up with H. LDPC codes are defined, you start with the parity check. You have J rows, in this case we have 5 rows, and you have N columns, N variable nodes. So the matrix, the parity check matrix, is as wide as your code word. So if you have a very long code, you're going to have a very wide matrix. And then each row is a parity check sum. How do you build this cool graph? Well, this is how we do it. You take the first row. You can see it's 1, 1, 1, 1, and we connect bit 1, 2, 3, and 4 to that node. This is going to be our node that stands for this row, and these guys here are going to be the bits that are present in that row. We do the same thing for the next row. We're starting to build our cool little graph that's going to help us do this math until we end up with this. And that's pretty satisfying. It looks lovely and symmetric. A regular code or regular graph means that the numbers of ones is constant for the rows and constant for the columns. It also means that all the code bits are involved in the same number of the sum nodes and vice versa. And this seems satisfying to us as designers, and it's very attractive looking when you draw them out. However, being irregular, meaning that some bits are involved in more sums and some sums are involved in more bits, that you have a difference, actually gives you an advantage. And the code, the LDPC code that was selected for DVB-S2 is an irregular LDPC. And you go, well, why would you do that? Well, if you cover some of the bits more than others, it actually lets you punch through and converge quickly on a result. You can overdo it, and you can get weird things like ringing, where it will never resolve or never converge. But being irregular actually gives you an advantage in LDPC. Maybe not with your body, but with the code, sure. So what do we do when we get data? You know, LDPC is scary. What do we do? Let's say that we get some data. These are actually voltages along the bottom that we've received. This is a code word that we've received. This is not a very big code. This is kind of toy LDPC. But you know, one that was 16,000 bits wide wouldn't fit on the slide. So we get this, we deliver it to these bit nodes at the bottom that we've connected all up. We're going to use something called a log likelihood ratio. Since we know the channel, we know what we are expecting to get, we can go ahead and make a guess. And because we know the type of noise in the channel model, we can go ahead and make that call. And we're going to do it. We're going to go ahead and assign a likelihood. It's not a probability, but it's a likelihood of what's what. So we can see here that some of these are really pretty clear. Like, if I'm expecting -1 or +1, you know, I'm expecting the 1.1s and the 1.2s to be pretty solid. One of these is wrong, by the way. One of those bits is an error. Okay, so we get a result, a log likelihood result. The neat thing about log is that you can just stay in addition, but it's kind of hard for us to deal with that, or at least it's hard for me. So I'm going to go ahead and convert it to what I'm going to call a probability, and we'll be multiplying. When you implement this in code, though, you really do want to stay in the log domain, just like in lots of other work. So I go ahead and do it. Since I know that probabilities add to 1, it's either a 1 or a 0, I know the likelihood of it being 1, and I know the likelihood of it being 0, and I will need to use both in the iterative receiver. And that's the real magic, is the iterations. Now here, what I've done is kind of color-coded to where the ones that I'm really sure about, the likelihoods that I'm really pretty clear on, I've made dark purple. And the ones where I'm a little wishy-washy or a little worried, I've made a little lighter, just so that you can see that there's a variety of results here. Now, our little bit nodes for our decoder, we've loaded up this particular set of probabilities there. And now, we're going to go ahead and send them to every sum, every parity check sum that we're connected to. So we send them up the edges of this graph. So let's go ahead and just focus on S1. Remember that this is going to be happening for 2, 3, 4, and 5, but we'll focus on this one in particular. Once we've delivered these probabilities, the other likelihoods, but more like probabilities, once we've delivered it up to this sum node, now we can do some work and some processing up there. I know for a fact that each one of these sums that's connected to various bits should sum to 0 if the code word is valid. And we know that just from general forward error correction, right? You run your result, and if you get a 0, that means it was a correct code word. It's in the null space of the generator. If I get a 1 as a result, I know that there's an error somewhere. Since I'm only connected to so many bits, you know, you can kind of tell which ones may be at fault. I get a 0 when I have an even number of 1s. and 0 is an even number. So okay, so here we have 3 that we're really pretty sure of, and 1 that actually I'm going to let you in on the secret. That's the one that's in error. Okay, so I have 4 results going to S1. So you know how it is. You have an even number of children, and 1 isn't really cooperating. S1 is going to do some processing, and then it's going to tell each of the bit nodes it's connected to how probable it is that they really are a 1. So it's like a parent listening to, the children rat on the other children, telling the one children that's misbehaving what the other children are saying so that that kid will change. And they're doing it for each kid. They're giving each bit the reports from the other bits. So hey, if variable node 4, let's assume it's a 1. And if it's 1, then there's either 1 more besides you, or there are 3 other ones. You're all 1s. You can't be the only one. And we can't have you be 1 and 2 others be 1, that would be 3. So it's like who's on first with 1s. Okay, so when you write this out in math to do this sort of processing, this is what it looks like. So this is just the likelihood. The black is the likelihood of that particular node being 1. And then we also have all the other cases where we have the zeros. This is just written out in math, what we recited on the other page. So each bit node gets a message formed from the probabilities from the other snitches, the other nodes. Okay, so we're going to go ahead and look at the results back to the nodes. For this particular node, we're going to get a result back of 0.35. Now these are marginals, likelihoods, kind of weird probabilities. And because we're going to slosh back and forth between the sums and the bit nodes, as an iterative receiver, this is where the magic happens. We're going to take many, many passes at this, and it's going to converge to be where you're sure we are okay, we've corrected the errors, or we run out of iterations. These codes have a max number of iterations, so you either converge and everything corrects itself with all of this work that we're doing, or you run out of time. This gets to be 0.35, this one's a 0.56, this is a 0.54. So we go ahead and report back. We've updated all those likelihoods. Now the real power is going to be in these cross connections. So you see, you're not just a member of this family that might get ticked off at you, but you're also a member of this family with all these siblings that might also get ticked off at you. And after a couple of iterations, you can see that everything is spread around and it's like spaghetti. This information from the other bits getting passed around is why this code is so good and why it's so fast. When we, as bit nodes down at the bottom, get that update after the sums all talk amongst themselves, you can see that I don't just get a result back from S1, but I also get a result back from S2. So the processing that's up here, the processing back up is now going to be this. We're going to take the channel result, our original channel result, we're still going to use that likelihood, and then we're going to use results from the other sums. So when we talk about this algorithm, which is called sum product, you can see why. It's a sum and a product, and then back to a sum, and then a product. Now the K is important. When you start multiplying different probabilities together, what happens? They're all less than 1, and you start multiplying things that are less than 1, then your product starts getting smaller and smaller over time. And you know how computers love that. They'll just run right out of bits, and you'll have nonsense results. So what you do in the iteration is that you renormalize. Because you knew the 1 and you knew the 0, the likelihood of both, then you can renormalize. They have to add to 1, right? And it's actually a fairly straightforward, cute little equation. Okay, so here's all the parity check nodes that are affected by these bits. Just to show you, we actually affect every one of the sums. They're all kind of connected. And eventually, everybody is snitched on each other. Going from the check node to the variable node starts the iteration again. And it continues until you succeed or you run out of time. And then you move on to the next code word. When you run out of time, that's when you shift out of those bit nodes your result. How fast you can converge, the tricks that you need to do it, and a lot of other stuff about LDPC is a very active area of research. If you type in low-density parity check codes to Google Scholar, you'll see tons and tons of papers with icky math. But what I've showed you here, the back and forth, the talking between the bit nodes and the sums, that is the heart of the best performing algorithm, the sum product algorithm. And that's actually the algorithm that came up in the original paper. So something about the story that kind of made me start thinking, it's like, well, if we missed this out there in published research, out in the literature, if we missed this for so long or overlooked it because of implementation challenges, how many other cool things that will take you up to some other limit in the many fields that we are part of, how much other stuff is out there? What being done today by a PhD student, maybe in here, might be this important. We're in Sierra A. We're running a DVB S2X block party to help put LDPC and lots of other things in the block diagram of this particular protocol into GNU radio. If you have an idea or experience in any of the sorts of things or any sort of feedback for us, please just walk in. We also have an SDR petting zoo. So we brought a whole bunch of SDRs, like as many as we could get our hands on. And we put googly eyes on them so to make them friendly because they're all like boring boxes and they need a little help to be a little more friendly. You know, they definitely don't look like nice old amateur radio rigs with tubes. They're not that pretty. So just come and visit and pet the SDRs. And check out our code. Our repository is fairly easy to find in GitHub. It's phase 4 ground. And the nonprofit that we formed is openresearch.institute on the web. Thank you. Any questions?
All right, Raphael. Oh, and if Michael, sorry, I don't know if it's Heinrich or Henry. Yes, okay, if we get you lavalier.
Thank you for the talk. That was a good walkthrough of belief propagation. I was wondering how you deal with encoding, because that's also very potentially computationally complex.
Yes.
And what's the structure of the code beyond it being irregular? Is it quasi-cyclic? Is there more stuff in the code that allows efficient implementations?
Yes, that's an excellent question. There's some things that you, let's see, I'm probably going to go try to answer your question backwards, and if I forget the first thing, I apologize. There's some caveats with the codes. You can design an LDPC code that follows the rules and is a crappy performing code. And it is because there is a lot of cyclic stuff in there. And for instance, in a graph, you count the number of hops that it takes for you to return back. If you have a path of 4, you are hosed. It won't do much. You need the girth, that's what it's called, of the code to be 6 or more. Hidden in there, though, I mean, that's kind of an obvious cyclic structure, but hidden in here is lots of the quasi-cyclic stuff, and there's tons of papers that go into this and testing that. LDPC is interesting because we're still finding out which factors lead to getting trapped in a local little loop. So you're right on the money. The answer, I guess, the short answer is yes.
Okay, so do you have the A-list published online too, describing the code?
Talking to the mic, won't get recorded.
Oh. Do you also have the A-list of the code that other people could look at it, or where could you find that? The describing of, I guess, the weights of, the row and column weights.
Yes, that's all published by DVB.
Okay, but is it a machine-readable format, or do you have to go through the PDF and
I hope you don't have to go through the PDF.
Okay.
Our volunteer that coded it up didn't have to. He had to go hunt it down, but it's there. But yeah, DVB does an excellent job of publishing all this stuff, and they've published their technical reports on this to describe their thinking and why they chose it over Reed-Solomon. Reed-Solomon was the choice for the first generation. And then your first part of your question, it was about the encoder. That's actually a big deal. The encoder for LDPC is actually very complex for all sorts of interesting reasons, because dealing with sparse matrices and everything. So it's kind of surprising. Usually the encoder is easy, and the decoder is where you have all the headaches. And I mean, it is a complex decoder, sure, but the encoder turns out to be enough of a hassle to where you really need to save LDPC for longer codes. where you basically pay off the overhead of that.
All right, we're out of time, I'm afraid. Thank you very much, Michelle.